What's up, elementary calc students? We are in chapter 5, section 3, where we're going to talk about higher derivatives, concavity, and the second derivative test. And higher derivatives are simply, well, so far we've been taking derivatives. And the very first derivative that we take is called the first derivative. Higher derivatives will be the second derivative, third derivative, and so on. How do you take the second derivative? You're going to take the derivative of the derivative. And the third derivative would be the derivative of the derivative, and so on. And we can use the second derivative in particular in order to determine concavity. So whether a particular part of the curve is sort of cupped in the upward direction, or if it is sort of, like a rainbow. Okay, so whether it's more like a cup or it's more like a rainbow, that's concavity. A cup is concave up, a rainbow is concave down. So the second derivative test is going to help us make some sense out of different parts of our curve. And remember that a rainbow, which is concave down, has a highest point. It has a maximum. And very often some information about that maximum point is valuable. And when a parabola is concave up, it has a lowest point, and certainly knowing when that lowest point is going to happen, or when the lowest, or what's happening at the lowest point, that information can also be valuable. So let's see what the first derivative in combination with the second derivative is going to illustrate for us. So higher derivatives, as we were talking about, simply involve taking derivatives of derivatives. And in this gray or sort of sand-colored box, we're seeing some different notations for the second derivative. The first notation that we see has f double prime of x. So it's got two of those little tick marks on there. And the next notation, it looks like d squared y. That tells us we're taking the second derivative with respect to x, and so on. So that third notation means the same thing. Typically, I feel like you're going to see f double prime. If you ran into an example where it was the third derivative, you might see f triple prime. But as it's saying here, once you get to the fourth derivative or higher, it's almost going to look like f to the power of x, and you'll just have to know what space you're in terms of whether or not you're taking derivatives, what that for really means. It's pretty infrequent that you're going to see that kind of a little exponent number, and it means take your function and raise it to the fourth power. If I were taking a function and raising it to the fourth power, I might have f of x, and I'd put it in brackets and put my 4 out here. In the first example, we're being asked to find the second derivative of this fourth degree polynomial. And let's just do that very quickly for practice. We've got f single prime, so the first derivative of x, take the exponent, multiply it by the coefficient, that turns into an 8. Keep the variable, decrease the exponent by 1. In the second term, take the exponent of 2, multiply it by the negative 7, we get negative 14. Keep the variable, decrease the exponent by 1. Derivative of a constant value goes to 0. So this is your first derivative. Second derivative, f double prime, is equal to, repeat the process, exponent times coefficient becomes a 24. Keep the variable, decrease the exponent by 1. This x value right here has an invisible exponent of 1, so the 1 times the negative 14 makes negative 14. Keep the variable, decrease the exponent by 1. Anything to the power of 0 is equal to 1, so really that says negative 14 times 1. No one's ever going to write that, so we'll get rid of that exponent and our variable, and what we have here is our second derivative. We will need to calculate second derivatives in order to extract some information from some graphs, maybe without even doing any graphing. So I'll put this text back on the screen for a second. The first derivative has been used to show where a function is increasing or decreasing. That's true. And where extrema or extrema occur. In other words, local maximums or local minimums. Those occurred at the point where the first derivative was equal to 0. We've done some testing for those. The second derivative gives the rate of change of the first derivative, which is the rate of change. So it's the rate of change of the rate of change. And it indicates how fast the function is increasing or decreasing. And I don't like this bullet. The rate of change of the derivative, in other words, the second derivative, affects the shape of the graph as shown. Yeah, I don't know. I don't know what that means. What I do know is that we're looking at the graph of an original function because on the vertical axis it says f of x. So I'm assuming that this curve is the graph of our function f. And you see some tangent lines on there. Those tangent lines express things related to first derivative, right? Instantaneous rate of change. Now the words that are written on there, concave down, you can see that the left-hand part of this graph is sort of cupped in the downward direction. The right-hand half of this graph is cupped in the upward direction. We say concave down and concave up, respectively. There's a point right in the middle where the concavity is changing, and that is referred to as an inflection point. Now this inflection point is actually a point on the graph, on the curve. We could find the coordinates of that inflection point. That won't always be the case. Our function here is actually defined at the inflection point. This inflection point has an x coordinate, maybe c, and our function is defined at c. We could find f of c. It's not always going to work that way. Let me give you a sketch of another function. Would you agree that this function right here is concave up? Doesn't it look like it's cupped in the upward direction? And would you agree also that the right-hand half of this function is cupped in the downward direction? I would agree with that. So that dashed line, that vertical asymptote that I drew, isn't that sort of when the concavity changes? On the left-hand side of the dashed line, it's concave up. On the right-hand side of the dashed line, it's concave down. So the dashed line represents where the concavity changes, or when, maybe is a better way to say, when the concavity changes. In this case, that vertical dashed line is at x equals 3. But is this function defined for x equals 3? It's not. It's an asymptote. There is no point on a vertical asymptote. So, a little bit tricky. Sometimes the function's defined for the x value when the concavity changes, and in this case, sometimes it's not. A point where a graph changes concavity is called an inflection point. It's concave up on an interval if the second derivative is positive. Okay, so what we're seeing in this bullet right here, and this bullet really right here, now we're relating the second derivative to concavity. So a function is concave upward on an interval if the second derivative is positive at each point on the interval. So let's look at this middle graph right here, and let's pick a point where our function is concave up. Now this point has its own x coordinate, let's say it's d, and if I took whatever that x value d is, if I plug that x value into my second derivative, f double prime, the number that would come out of f double prime would be a positive number. I know that it would be a positive number because at that point on my graph, the graph is concave up. It works the other way. If I didn't know what the graph looked like, but I knew that the second derivative was positive, I would know, without even seeing the graph, that the graph at that point would be concave up. Our graph is also concave up here, and it's concave up here, and it's concave up here. It looks like our graph is concave up on the interval starting at c and going all the way off to positive infinity. This graph also looks like it's concave down everywhere to the left of x equals c. So I would say that it's concave down from negative infinity all the way up to c. Notice that both of those intervals are open intervals. C has a parenthesis next to it. We're not including the inflection point. That's the point where concavity changes. It's neither concave up nor concave down. So you might be asking, well, what would happen if you took the x value of c and you plugged it into the second derivative? Well, if it's concave down, you get a negative number. And if it's concave up, you get a positive number. And if it's neither concave up nor concave down, the second derivative will either be 0, which it would be here, or your second derivative would be undefined because your function is undefined there anyway, as is the case when you have a vertical asymptote. So there's a test for concavity. We pretty much just talked about it. F is a function, first derivative and second derivative exist. F is concave up on an interval if the second derivative is greater than 0, concave down on the interval if f double prime is less than 0. Exciting. This, however, gets a star, an inflection point for a function f, or at an inflection point for a function f. The second derivative, as we mentioned already, is either 0 or does not exist. That should be in your notes. These two diagrams should be in your notes. The pre-printed diagram has an inflection point where the second derivative is equal to 0. You could draw an arrow into here and you could say f double prime, that's double prime right there. Ugh. Sometimes the digital pen is not as precise as I'd like it to be. F double prime of c here is equal to 0. Now over here, f double prime of, in this example it was a 3, is undefined. So that corresponds to what I put a star next to right here. And in example number 2, we want to find the largest open intervals where this function is concave up and where it's concave down. Now, if you know your functions fairly well, especially the reciprocal function 1 over x, then you would have a pretty good idea of what the graph of this function looks like anyway. However, let's pretend that we have no idea what it looks like. We're trying to determine concavity, so I want to know where on this function is my second derivative greater than 0, and where on this function is my second derivative less than 0. Let's try to find the place where the second derivative is 0. Let's find that dividing line. Let's find that inflection point. If there is one, maybe we're finding an inflection point, maybe we're finding a place where our function is not equal or is undefined. Ooh, actually, if I just look at this function, I've got a strong inkling of where or when our function is undefined. I'm pretty sure that an x value of -2, which would cause division by 0, which would cause a vertical asymptote, I'm pretty sure that that's where we're going to see our inflection point, or at least an x value that corresponds to where concavity changes. I'm going to make that assumption, but I'm just going to hold it in my mind. I still need to take the second derivative in order to determine where to the left of x equals -2. Is it concave up or concave down over there? I have to take the second derivative in order to make that determination. So let's find the second derivative. Well, first we need to find the first derivative. F prime is equal to, well, we could use the quotient rule. That kind of stinks. I think what I'm going to do is I'm going to rewrite my original function. Let's actually erase the prime on this thing. let's rewrite f of x as 3 times x plus 2 to the negative first power. And then we can take the derivative of that using the power rule. I'll take the exponent, multiply it by the coefficient, which makes it negative 3. We'll keep the expression the same, that's an x plus 2. We'll decrease the exponent by 1, and then we'll multiply by the derivative of the inner function, which is x plus 2. What's the derivative of x plus 2? Just 1. So we don't really need that. So that's our first derivative. Now let's find the second derivative. F double prime of x is equal to, take the exponent, multiply it by the coefficient. Negative 2 times negative 3 makes positive 6. Keep the inner function. Decrease the exponent by 1. Multiply by the derivative of the inner function. No one would actually write times 1. So this is our second derivative. We could rewrite this as 6 over x plus 2 to the third power. Will this function, our second derivative, ever equal 0? No, because the only way for a fraction to equal 0 is if the numerator equals 0, and I don't think 6 is ever going to equal 0. So maybe we have an inflection point where the function is undefined. It's undefined when x equals negative 2 because that would cause division by 0. So that's probably our inflection point. We already knew that, but now we've confirmed it. So let's test an x value that's to the left of x equals negative 2, and we will test an x value that's to the right of x equals negative 2. So let's test x equals negative, let's make it negative 3. Since I said we were going to test to the left first, let's test to the left of x equals negative 2. That's an x value of negative 3. We need f double prime of negative 3. F double prime of negative 3 equals 6 over negative 3 plus 2 to the third power, which equals 6 over negative 1 to the third power, which equals negative 6. Negative 6 is less than 0. Therefore, I wish that I could cut and paste. Can I cut and paste with this? No, that didn't do it. What about if I long press on that? No, that didn't help. What about this? I can draw shapes. That's nice. What about this? That's going to let me insert pictures. Okay, so I can't. Since negative 6 is less than 0, concave down. Concave down where? Or concave down when, you might say. This graph is concave down for all x values less than or left of x equals negative 2. So it's concave down on negative infinity up to negative 2. Then let's test x equals negative 1, which is to the right of negative 2. This time I'm going to wise up and write this down here. F double prime of negative 1 is equal to 6 over negative 1 plus 2 to the third power, which equals 6 over 1 to the third power, which equals 6, which is greater than 0. Therefore, concave up on the entire interval that's to the right of negative 2. In other words, from negative 2 all the way up to positive infinity. That's not so bad. you should take this equation, the original equation f of x, and type it into a grapher, either a graphing calculator or desmos.com or whatever other graphing utility you like to use, and see what this thing looks like. It's going to look a lot like my graph that I drew to the right here, except the vertical asymptote will be shifted to the left 5 units. It'll have a vertical asymptote at x equals -2. Concave up everywhere to the left of it, concave down everywhere to the right of it. This says concave down to the left. Is that true? Oh, yeah, that's okay. Right, so this looks good. Nice. The second derivative test, the idea of concavity can often be used to decide whether a given critical number produces a relative max or a relative min. It's an alternative to the first derivative test. So let's just say, hypothetically, that I give you a function and you took the first derivative, set it equal to 0, and found that the first derivative, f prime of x equaled 0 when x equaled 5. That means that your original function, f of x, has a horizontal tangent line at the point on the curve when x equals -5, which means that it's possible that when x equals 5, you're either at the top of a hill or at the bottom of a valley, which means you're at a maximum or at a minimum. But which one is it? How are you supposed to determine? Well, we've done tests before where we then check the first derivative to the left of and to the right of x equals 5. And if our first derivative is less than 0, in other words, we're decreasing to the left of 5, and then increasing to the right of 5, then this point right here where x equals 5 is probably a minimum. And if our first derivative was positive to the left of 5 and negative to the right of 5, then when x equaled 5, we probably had a maximum. Is it possible that it could have been increasing to the left and to the right of x equals 5? Absolutely. What did that mean? It meant that there was no extrema at that point. There was no max or min where x equaled 5. And that happens every once in a while. Like if your graph looks like this. At this point right here, you do indeed have a horizontal tangent line, but that's not a max or a min. So that's how we would test for relative maximums and minimums using the first derivative test. Now we can use our second derivative test. And if we know that at this point we have a horizontal tangent line, in other words, f prime is equal to 0 at that point, we take this x coordinate, we plug it into the second derivative, and if it turns out to be negative, if the second derivative turns out to be negative, we know that it's concave down. And if it's concave down, then it's a maximum. If it had been concave up at that point, then that point must have been at the bottom of a curve, in which case it's a minimum. That's what's articulated in this gray box right here. We're assuming that f prime of c is equal to 0, and then we test. If f double prime of c is greater than 0, then it's a minimum. If it's less than 0, then it's a maximum. If f double prime is equal to 0, or it does not exist, then the second derivative test hasn't told us squat, and we should probably back up and try the first derivative method for examining what's happening when x equals c. Yeah, you can read that bullet. It's not working. You can read that bullet. You can read the third bullet. And let's go into this example. Let's decide if x equals 2 is a critical number. Remember, a critical number is going to be a max or a min. And if so, decide whether the point is a relative minimum, maximum, or neither. Great, so how am I supposed to determine if it's a critical number or not? The first derivative should equal 0 when x equals 2, if indeed x equals 2 is a critical number. Let's take the first derivative. F prime of x equals 6x squared minus 6x minus 12. We could set this equal to 0 and solve, or we could just evaluate f prime of 2. Not f double prime, just f prime of the actual number 2. There we go. Equals 6 times 2 squared minus 6 times 2 minus 12. That's equal to 4 6s minus 2 6s minus another 2 6s equals 0. So we know that this has the potential to be a maximum or a minimum. We know that the slope of the tangent line to the curve at the point where x equals 2, we know that the slope of the tangent line at that point is equal to 0. Slope of the tangent line at x equals 2 is 0. Now let's determine if that point is a max or a min. We're going to take that x value of 2 and plug it into the second derivative. If the second derivative kicks out a number that's positive, then it's concave up, which means we're working with a minimum. If the second derivative kicks out a negative number, then it's concave down, which means we're looking at a maximum. If f double prime of 2 is equal to 0, then we haven't learned anything, and we're going to have to back up and use the first derivative method of examination. F double prime of x is equal to 12x minus 6. F double prime of 2 is equal to 12 times 2 minus 6, which is equal to 18, which is greater than 0. Therefore, concave up. Therefore, there's a minimum at x equals 2. Nice. Here's an application. This is a pretty legitimate application. It's subtitled Diminishing Returns. And what we're seeing here is a graph, and there's a particular point on the graph that's being highlighted. It's an inflection point. Everywhere to the left of that point, our graph is concave up. Everywhere to the right of that, our graph is concave down. Now, before we get too far into this, let me ask you a little sub-question. I'm going to draw you the graph of the value of a stock, of an investment, okay? While I'm drawing the curve, you be thinking, should I stay invested or should I sell the investment? Value of my investments going up. Values of my investments going up. Are you staying in? I would stay in. Value of the investments going up, and then it's starting to level off. Now might be a good time to sell, because it's possible that it could start swooping in the upward direction again. I mean, it's still going up, it's just not going up as fast. But what's possible is that we're about to head in this direction, and we're going to really regret that we hadn't gotten off of that train earlier. But it's this point right here that's the inflection point. It's when, as I continue investing money in the business, yes, the business is still making money for me, but it's not making money as fast. Here, it's making money really fast because the slope of my tangent line is very positive, right? It's not just a positive 1, maybe it's a positive 50, right? The slope of that tangent line. But here the slope of the tangent line is only 40, and here the slope of the tangent line is only 30. And pretty soon I'm going to reach a point where I'm going to invest some money, and all I'm going to do is get my money back. I don't want to just be handing somebody money for them to hand me my money back. That's not a very good use of my time. So the ideal time to get out is this point right here. Not so much as pertains to investments, although technically it's an investment, but really it's like if I own my own business, do I want to continue putting money into the business if those dollars are not earning me as many dollars back as they used to? And we call that point the point of diminishing returns, because the return on our investments starts to decrease or diminish. So everything that's in, you can read all of this stuff. It's what we just talked about, which drops us into this example problem, which is our last example and last problem for the section. And we want to find the point of diminishing returns as an ordered pair x comma y for this revenue equation r of x, which is equal to blah blah blah. And we're going to be examining that revenue equation on the interval where our x values are between 0 and 20. This revenue equation represents revenue in thousands of dollars. X represents the amount spent on advertising in tens of thousands of dollars. So we got a couple of different scales there. How do we find the point of diminishing returns? We're going to need to figure out where the concavity changes. Where the concavity changes from, in this case, probably where it changes from positive to negative. That will be our point of diminishing returns. So let's take the second derivative of this thing. R prime is equal to, the derivative of 3,000 goes to 0, so I'm actually going to write a 0 this time. The derivative of our next term, negative x to the third, is going to equal negative 3x squared. Of our next term, positive 36x squared, that will become a positive 72x. Last term, plus 700x becomes plus 700. I like this. Now it's in the correct order. Really, I could just scribble out the 0. That's not helping me much, but keep that minus sign so that it's negative 3x squared plus 72x plus 700, and let's take the derivative again. R double prime of x is equal to negative 6x plus 72. Great, so that's our second derivative, and I'd like to find where my second derivative is equal to 0. So let's set it equal to 0. Subtract 72 from both sides. Divide both sides by negative 6. Wait, 9 would be 54, sorry. Y'all know that arithmetic's not my strong suit. 12, there we go. So what that means in the context of the question is that we start experiencing diminishing returns, or we will start experiencing diminishing returns if we spend more than 12 tens of thousands of dollars on advertising. That would be 12 with 4 zeros after it. That's a lot of money to spend on advertising. Find the point of diminishing returns. So we want this to be expressed as a point. And this is an x value, which really translates to 12 with 4 zeros after it. That's an x coordinate. Let's find the corresponding revenue value. We can find that by taking the 12 and plugging it into our revenue equation. And I have zero interest in doing that. You do that. While you're doing that, and you could just punch it into a calculator. I'm just lazy and I don't want to do it. You do it. You do the heavy lifting. I did everything else. The last thing I wanted to show you is I went and I graphed this equation in Desmos, which is the easiest place for me to show you what the graph of it looks like. And of course, it's been erased. Why is it erased? I can't even go back to it. Terrible. Well, I want to show it to you anyway. I'm going to come up into, I'll pause it while I type in. You don't have to watch me typing. Okay, so I've typed it in, and of course it's behind my head. But if I hide myself, I'll miss you. So let me see if I can just move me out of the way. There we go. So I typed in this equation up here that's right above me now. I typed it in as a y=, equation, and let me slide this off the screen now. There we go. So it's a y= equation, and yeah, I don't know, I hit enter and I don't see anything. Now these numbers are big, right? The negative x to the third isn't so big, but positive 36x squared plus 700x, and then all the way to the left there's a positive 3,000. That's probably a vertical shift of 3,000. I'm going to start zooming out. So on Desmos, if you're using a laptop, maybe you could pinch to zoom out. And that's what I'm doing. Oh, finally, I see a red vertical line over there. But since this is a third-degree polynomial, this thing should look like kind of a squiggle. Oh, did I type this in right? I'm pretty sure I did. I just want to double check before we keep talking about it. There's the 3,000 minus x to the third plus 36x squared plus... how do I screw that up? It should say plus 700x. It says plus 700x. Okay. So, geez, this thing goes... Whoa. This thing goes way up here. How far up does this... I don't even know. Okay, let me keep zooming out, maybe. Ooh, I think I see a slight variation in the line right there. Let's start zooming in on this. And yep, okay, I think I see a little peak right here. So I've zoomed in on what looks like a maximum point right here. Now, we're supposed to be looking at this function between x values of 0 and 20. So in the top right corner of the screen, you can barely see it up there, there's a little wrench above the plus sign. I'm going to click on that, and a little more than halfway down it says x-axis. And below that, I'm going to click and change this number to a 0, and I'll change the right-hand number to a 20. And then I just sort of tapped in the middle of the screen. And the problem is I don't see anything anymore. So I'm going to, now it shouldn't have changed the vertical sort of aspect of what I was looking at, it just changed it horizontally. So I'm going to zoom out again and see, oh, there's a bit of a curve there, okay. But that's too far to the right. I really want to be looking at this thing from 0 to 20. Can I zoom out far enough to be able to see? Man, I have to zoom out really far. Still. Let's see. So having zoomed out that far, I can almost see, oh, there's the x-axis. Okay, so it's starting to look a little bit better. I've got that relative maximum point near the top right. I've got a relative minimum that's down there pretty close to the origin. I'm going to click on this wrench again in the top right corner, and I'm going to change my x values again to go from 0 to 20. Enter. Oh. Alright, so you see what's happening to the shape of this graph? It's the same graph, I'm just changing the scale of the vertical and horizontal axis. Horizontally, I'm currently going from negative 50 to like positive 70 almost. But vertically, I'm looking at like negative 80,000 up to well over 100,000, pushing up like to 100 and maybe 30,000. So the scale is a little bit tough to relate to. But let's zoom back in because I'm really interested in, oh, let me point out another thing. Can I highlight a particular point? Can I just get that point to stay there? I can't. All right, I'm just going to hold my pen right here. It's kind of moving around a little bit, but that's okay. everything that's to the left of this point right in the middle of the graph that I'm trying to hold on to, everything to the left of there looks like my graph is concave up. And everywhere to the right of this point, it looks like my graph is concave down. And the coordinates of the point that I'm holding fairly steady on are right around 14. It looks like the place or the time when I would change concavity would be at the point where my x value is approximately 14. And in fact, we found that it's actually at the point the concavity changes where x is equal to 12. Now, I don't know in Desmos how to sort of specify that point just freehand, but just so that you have a visual idea of what this graph looks like and that this is indeed the point where concavity changes, I thought it might be helpful for you to have the visual. In Desmos, you have the opportunity. On the left-hand side, I've clicked and I'm going to type in one more equation. Instead of typing in a y equals equation, this time I'm going to type in x equals 12, which is going to draw a vertical line, which does allow me to click on the point of intersection. And what I'm seeing there is an x coordinate of 12 and a y coordinate of 14,856. And what that means is that when you plugged 12 into your revenue equation, you should have gotten out a revenue value of 14,856. If you didn't, you might have made a mistake with your arithmetic or just typing it into the calculator. So double check that. And with that, I'm going to leave you. That is the end of that section. And we've got one more section left in this chapter. So I'm going to head over there and I'll see you there.